Hello dear guys, welcome back to our physics class. Today's lesson we are continuing to explain section 2 in chapter 2 about the properties of the solid. In the previous lesson we studied the phase of matter. So if you remember, we had 4 phases of matter: solid, liquid, gas and plasma. And the plasma is the fourth state of matter that achieved at a very high temperature and consists of atomic nuclei with the electrons moving very fast at a high speed. And after that, we studied in section 2 the properties of the solid, the rigidity, elasticity, and also we studied the tension. So we stop it here in Hooke's law. What is the Hooke's law statement? Robert Hooke proved in the 17th century that the tension in a spring is directly proportional to the elongation. When the tension increases, the elongation of the spring or wire also increases. The relation between elongation and tension is directly proportional. And according to Hooke's law, tension is equal to K times elongation. What do I mean by T? The capital T represents for the tension measured in Newton, and K is a spring constant measured in Newton per meter. So the spring constant describes the stiffness and the flexibility of the spring. More K, it means that the spring is very strong. Okay, so less K, it means that the spring is very thin and very flexible. And L minus L naught, this is elongation. The amount of the the amount of the stretching and compressing of the spring and wire under the tension. According to this equation, we can see that at constant K, when K is constant at a given spring, the amount of the tension is directly proportional to the elongation. When the tension gets small, what happens to the elongation also increases. The relation between tension and elongation is directly proportional. According to Hooke's law, tension depends on what? Spring constant and elongation. So we can rearrange this equation to determine K. K is equal to what? What we have with spring constant? Elongation. It goes to the denominator, and the tension goes to up. Okay, so according to this equation, K measured in what? Tension measured in Newton, elongation measured in what? In meter. What is the SI unit of spring constant? Newton per meter. So spring constant can be measured with which of the following? Newton per meter. For example, if I bring in the exam, you have to choose Newton per meter. When a metallic wire is under tension, assume that this wire is under tension. What is this? This is tension, and this is wire. When a metallic wire is under tension, its elongation depends on what? Its elongation depends on what? Guys, be careful. The elongation of a wire or spring under the tension depends on 4 factors. The first factor is the amount of tension. When the tension gets more, elongation also increases and also becomes more. Okay, so the relation between tension and elongation is directly proportional according to Hooke's law. The second factor that affected the elongation, the length of wire. So when the length of wire increases, what happens to the elongation? Elongation also increases. The relationship between elongation and initial length and the length of the wire is directly proportional. As you can see in this figure, guys, how many wires do we have? We have 2 wires. And the 2 wires is under the same tension. Both wires, they have the same tension. But which wire has more elongation? The wire with the more length or the wire with the small or short length? Absolutely, the wire with the more length has more elongation. Why? Because the length of the wire is directly proportional to the elongation. The third factor is, guys, look. The third factor is the radius of the cross-section of the wire. But with the radius of the cross-section of the wire is inversely proportional. For example, if you have 2 wires with the same material and same length under the same tension, but one wire is thick and the other wire is thin. Okay, one wire is thick wire, it has more cross-section area. Like, for example, we have 2 wire, okay? Sorry. Assume that we have 2 wires. Okay, and another wire is a thin wire. Both of them, they have the same tension. Okay? Tension, tension. 10 Newton, 10 Newton. The length of the wire, like 2 meter. Length of wire, 2 meter. Both wires, they have the same length. They have the same tension and they have the same material. Okay? But which wire has more elongation under the same tension and the same length? The thin wire or thick wire? This is thin wire and this is thick wire. Which one has more elongation? Absolutely the thin wire. This one has more elongation. This one has more elongation, but this one has less elongation. Okay, so the reason now I'm going to explain what is the reason why the wire with the more cross-section area has less elongation while the wire with the thin cross-section area has more elongation. We have this question now. I'm going to explain after this. And the fourth factor is the type of the material. The type of the material also affected the elongation of the wire. Okay. Another topic is strain. In a previous lesson, we studied a little bit about the strain, the ratio between elongation and initial length. What is strain? The ratio of between elongation and initial length. This is strain. The symbol of strain is epsilon. Epsilon is equal to what? The ratio of elongation over what? Over initial length. And strain is unitless. Why strain is unitless? Because strain is the ratio between two lengths. Elongation measured in meter. Initial length also measured in meter. Meter with meter cancel. So that is why strain is unitless. The strain is the amount of the elongation per initial length of the wire. Why strain is unitless? Because there's a ratio between two lengths. Consider two wires of the same cross-section area and material, but different lengths, attached to two identical masses, same tension, to their extremities as in the figure 215 as shown here. Which wire has more elongation, guys? We have two wires, same tension, same material, but different length. The wire with the more length has more elongation, or with the wire with the small length and the short length has more? The wire with the long length, the longest wire has more elongation. The wire with the longer length will have more elongation, because elongation is directly proportional to the length of the object and of the wire, and there are constant stress on force parent area. So guys, in this case, we have two types of the spring: series springs under tension and parallel springs under tension. Look. Series springs and parallel springs. In a series springs, for example, if we have three springs connected one by one, okay, so this connection of the spring is what? Is the series connection. So in this type, when there's three springs or four springs, okay, connected in a series connection, as we can see in this figure, the amount of elongation becomes more and more. Why? Because when the spring connected in a series connection, its length gets more. So when the length gets more, elongation also becomes more. So it has more elongation. Okay, it has more elongation. In the springs connected in a series, where there will be more what? There will be more elongation. Why? For given forces compared to the series connection, such as the figure here. Okay, we have two springs. The first two springs connected in a series connection, and the second one, three springs connected in a series connection. Which one has more elongation? Two springs series connection or three springs series connection? Absolutely, the three springs are connected in a series connection has more elongation than the two springs. So the tension, like in this case, the tension is equal to the same tension that given in the question. Okay, we do not divide the tension by the number of springs. Okay, but in parallel connection, the situation is completely different, guys. The situation of parallel spring is completely different with the series connection. In a spring is connected in a parallel connection, there will be less elongation. This case more elongation, but this case less elongation. Assume that this is tension. Okay, so the tension for all springs, tension of all springs. Okay, in a parallel connection, the elongation is less than comparing with the series connection. In parallel connection, there will be less elongation. Okay, so in a parallel connection, the tension is distributed of to the number of springs to determine the like Hooke's law and the amount of elongation. Guys, in a parallel connection, you have to determine the tension because this tension is distributed for all of them. For example, if the tension is here is 15 Newton, guys, this 15 Newton is distributed over the 3 springs to determine the amount of tension T for all of them divided by number of springs. How many springs do we have? 3, okay? Number of what? Springs in parallel connection. Only in parallel connection, you have to divide the given tension divided by number of springs. Only in parallel connection, but in series connection, we do not we do not divide the tension by number of springs. Tension here is equal to T without division. But here in parallel connection, we have to divide this tension by what? Number of springs. In this figure, how many springs do we have? We have 3 springs. What is the value of tension? 15. 15 divided by number of springs is equal to what? 5 Newton. To solving the question according Hooke's law, you have to use this 5 Newton, not 15. Okay, only in parallel connection. In parallel connection, you have to divide it, the amount of tension by number of springs. If you have 2 springs, you have to divide by 2. If you have 4, you have to divide it by 4. And also I wrote here as a note, in parallel connection, the tension is distributed to the number of springs, and tension is equal to the given tension divided number of springs. Look at this question, guys. Which one has more elongation? A thick wire or thin wire of the same length, same material, and same tension? Absolutely, the thin wire has more elongation. The thin wire has more elongation. Why? Because thick wire weight is distributed over a large area. The weight and the tension of the thick wire distributed over the large area of the cross-section of the wire. So, before solving the question, guys, we have some important tips and notes. The student must know about this note. The SI unit of area is meter square. What is the SI unit of area? Meter square. And SI unit of radius is what? Meter. Cross-section area of wire, A of wire, is equal to what? Is equal to pi r square. How can you determine the area of the wire? By using this relation. When radius is given, you have to convert to area. How? Pi r square. When radius is given, how can you determine area? Multiply by pi and r square. Okay. If the radius of the wire is given, you can find its area by using this relation. If diameter of the wire is given, you should change into the radius then to the area. Like for example, if the diameter is given, like for example 2 meter, okay? So you have to convert this diameter to what? To radius, and the radius to what? To area. How can you convert diameter to radius divided by 2? D divided by 2. 2 divided by 2 is equal to 1 meter. How can you convert radius to area? Area is equal to pi r square. Pi 3.14, r 1 meter square is equal to 3.14 meter square. So this is very important, guys, be careful. When diameter is given, we don't need diameter to solve a question. We have to convert diameter to what? To radius. How? Divided by 2. After that, when you find the radius, you have to convert to what? To the area. How? By using this relation, the area of the cross-section wire is equal to pi r squared. And about the conversion, so we have some important converting. We studied in chapter 1. How can you call this? Is just for reminding you guys, centimeter to meter multiply 10 power negative 2. How about centimeter square to meter square multiply 10 power negative 4. Centimeter cube convert to meter cube multiplied by what? 10 power negative 6. Okay, so this is very, very important, guys. Pay close attention, please. This converting is very important. And so what about the millimeter? When millimeter is given, like millimeter to meter multiply 10 power negative 3. Millimeter square to meter square multiply 10 power negative 6. Millimeter cube convert to meter cube multiply 10 power negative 9. So this is very important. You have to keep in your mind. In this way, you can convert all the units. Okay. The last topic in this section, guys, the Young's models. What is Young's models? The Young's models, the ratio of the stress to the strain of a given material. The ratio, Young's models, E capital is the symbol of Young's models. Ratio, what do you mean by ratio? Fraction. Between what? Stress to strain. Stress to what? To strain. Okay? Young's models is the ratio between what? Stress to strain in a given material. SI unit of Young's models is Newton per meter square, which is equal to what? Pascal. What is the SI unit of Young's models? Pascal. It is equivalent unit is what? Newton per meter square. They have the same unit of stress. They have the same unit of pressure. Okay? Guys, in this equation, you can determine the amount of Young's models. But in the case when the stress and the strain are not given in the question, how can you determine the Young's models? The question must give you the other quantities. Like, for example, stress is equal to what? Tension over area. Strain is equal to what? Elongation over initial length. By substituting into the main equation here, look, guys, by substituting into the main equation, Young's models is equal to what? And instead of stress, write down what? Tension over area. Tension over area. And instead of strain, elongation over initial length. According math basic, so you have to convert this fraction into the multiplication. What is remain? Tension over area multiplied by what? Reciprocal L naught divided by initial length. So finally, Young's models is equal to what? T times L naught, TL naught. A times elongation, A times elongation. Okay? So in this case, you can determine the amount of the Young's models when tension, initial length, area, and elongation are given in the question. When does this equation can be used and when does this equation can be used? Both of them, guys, be careful. Both of them can be used to determine what? The amount of Young's models. When does this equation can be used? When stress and strain are given in the question. Okay? But if the stress and strain are not given, you have to use this relation. So, how many equations do we have? 2. Stress over strain, tension times initial length over area times elongation. Guys, look. How many variables do we have? We have 5 variables. Young's models, tension, initial length, area, and elongation. Okay? Like, if you cross multiply this equation, sorry. T times L naught, A times initial. What we have here? 1. Cross multiply. 1 times TL naught, TL naught. E times A times elongation is going to be E times A times elongation. We have 5 variables, so we can make 5 different equations. Like, for example, if the question asks us to find elongation. So, bring down elongation and make a fraction, always. Between elongation, between young models, area and elongation, we have multiplication. In the case of multiplication, to determine the amount of elongation, the youngest models and area is always goes to the denominator. Okay, so the quantities with the unknown value always located down and located in the denominator. What is remain? T times initial length remain here. To determine like tension, how can you determine tension according the youngest models? Guys, look. What we have what is unknown? Tension. Bring down tension and make fraction always. Okay. What we have with the tension, but you have to make sure that between them is multiplication. Okay. What we have with tension? Initial length. What is remain? E times A times elongation. And for the other quantities, you have to do the same thing. It is very important to rearrange the equation to determine the quantity that unknown in the question. Okay, guys, look at the sample problem 2b. Sample problem 2b. The question says a steel wire of diameter. What is this 0.4? This is diameter. Diameter is given in millimeter. 0.4 millimeter. Guys, be careful. Not allowed solving question with the millimeter. You have to directly convert to meter. How can you convert millimeter to meter? Multiply 10 power negative 3. So diameter is equal to what? 0.4 times 10 power negative 3 meter. This is diameter. Initial length 2 meter. L naught 2 meter. Suspended vertically from a fixed point and weight 80 Newton. 80 Newton, this is tension. How did you know this is tension? Because we have wire and the tension measured in Newton. Because of the unit, you can recognize that this is tension. How did you know this is tension? By the unit. Connected to its lower end, and the resultant elongation of the wire is 6.4 millimeter. The amount of elongation also given in this question, 6.4 millimeter. You have to convert to what? To meter. Multiply by 10 power negative 3. It's gonna be what? 6.4 times 10 power negative 3 meter. This is elongation. Calculate youngest models. What is unknown? The youngest models unknown. For every solving question, guys, be careful. You have to write down the given value and the unknown in the question at first. Okay? For every solving question in physics, you have to write down the given value and the unknown value in the question. After that, you have to think which equation can be used to determine the youngest models. You have to write down all equations and which equation is suitable to determine the amount of elongation, because physics is like a key. If you have a key, you can open all the locked door. Okay? So in this case, the youngest models unknown. Guys, look. How can you determine the youngest models? According to this relation, youngest models is equal to what? Stress over strain. Can I use this relation to determine youngest models? No. Why? Because we don't have stress, we don't have strain. Another equation. If you remember, we studied another equation of youngest models when strain and stress are not given. Use this relation. Tension times initial length. Area times elongation. Guys, look. Do we have tension? Yes. Do we have initial length? Yes, 2 meters. Do we have area? No, we don't have area. Do we have elongation? Yes, we have elongation. Only we don't have area. But instead of area, what was given in the question? Diameter. How can you convert diameter to area? We studied. Diameter, you have to convert to radius. Radius, convert to area. How can you convert diameter to radius? Divide by 2. How can you convert radius to area? Pi r squared. Okay? Radius is equal to what? Diameter divided by 2. Diameter was given 0.4 times 10 power negative 3 divided by 2 is equal to 0.2 times 10 power negative 3 meter. What is this? This is radius. Okay? So radius is equal to what? Radius is equal to 0.2 times 10 power negative 3. Convert this radius to what? To area. Area is equal to what? Pi r squared. 3.14 times 0.2 times 10 power negative 3 squared. Area is equal to what? By calculator, you can determine the amount of the area. Okay, now I'm going to calculate. 0.2 times, sorry, is equal to like 0.2 times 0.2 times 3.14 is equal to this number, and I got this number, guys, 0.100,256 times 10 power negative 6 meters square. What is this? This is area. So can you replace into this equation? Yes. After we found the amount of area, we can substitute into this equation to determine the Young's modulus. Young's modulus is equal to what? Do we have tension? Yes. 80. Initial length 2 over area. Do we have area? We didn't have, but we found 0.1256 times 10 power negative 6 times. Do we have elongation? Yes. After converted to meter, 6.4 times 10 power negative 3. So by calculating, you can get the amount of the Young's modulus, which is equal to. Now I'm going to do it. Okay. Times is equal to 0.8 times 10 power negative 9. 80 times 216. So Young's modulus is equal to divided by 0.8 is equal to 200. So it's gonna be 200 times 10 power. You have to move the 10 power negative 9 goes up. It's gonna be positive 9 Newton per meter square. Or you can say Young's modulus is equal to 2 times, we have 10 power 2 plus 10 power 9 is going to be 11 Pascal. What is the value of Young's modulus? 2 times 10 power 11 Pascal. In this way, you can determine the amount of Young's modulus. Okay? So you can screen this answer. Practice 2B, guys. Look at the question 1 in practice 2B. Okay? A metallic wire of diameter 1 millimeter. Diameter also given in this question. Diameter is equal to 1. Diameter was given 1 millimeter, which is equal to 1 times 10 power negative 3 meter. Radius equal to what? Diameter divided by 2. 1 times 10 power negative 3 divided by 2, 0.5 times 10 power negative 3 meter. What is this? This is radius. Length 2 meter. Initial length 2 meter. 2.3, sorry. 2.3 meter. Made of a copper. Young's modulus 1.1. Young's modulus given 1.1 times 10 power 11 Pascal. Okay? What is unknown? Calculate the cross-section area of the wire. We have two unknowns in this question, guys. A, calculate cross-section area of wire. How can we determine area? Area is equal to pi r squared because we have radius. The diameter was given, but we converted to radius divided by 2. Is equal to 3.14 times 0.5 times 10 power negative 3 square. Area is equal to what? 0.5 square times 3.14, 0.785 times 10 power negative 6 meter square. This is area. The area of cross-section wire is equal to 0.785 times 10 power negative 6. This is branch A, guys. Branch B, calculate the strain in the wire for elongation. Elongation was given. Branch B, guys, look, in branch B, elongation was given is equal to 0.85 millimeter convert to meter, multiply 10 power negative 3. Multiply 10 power negative 3 meter. This is elongation. Calculate strain. What is unknown? Strain. How can you determine strain? Strain is equal to what? Elongation over initial length. Do we have elongation? Yes, was given 0.85 times 10 power negative 3 divided by 2.3. Okay, 2.3, which is equal to what? 0.85 divided by 2.3 is equal to 0.37. 0.37 times 10 power negative 3 unitless. 0.37 times 10 power negative 3 unitless. It has no unit. Why? Because there's a ratio between two lengths. Also, you can screen this, the solving of question 1 in practice 2b. Question 2 in practice 2b, guys. In exercise number 1, this question related with the question 1. We can use the given value of question 1 in question 2. Calculate stress of the wire. What is unknown in question 2? Stress of the wire. How can you determine stress? Stress, we studied that is equal to tension over area. Look, guys, do we have area? Yeah, we didn't have, but we found. Okay? We have area. So do we have tension? No. We don't have tension, guys. Because we don't have tension and stress also unknown, we cannot use this relation. Another relation that including the stress. If you remember, Young's modulus is equal to stress over what? Strain. What is unknown? Stress. Cross product. 1 times stress, stress. Strain times Young's modulus, strain times Young's modulus. Stress is equal to what? Strain, we didn't have, but we found. Look, 0.37 times 0.37 times 10 power negative 3 times. Do we have Young's modulus? Yes, 1.1. 1.1 times 10 power 11. Stress is equal to what? Is equal to, now I'm going to tell you, 0.37 times 1.1. 0.4 times 10 power 10 power 8 Pascal, or you can say 4 times 10 power 0.4 is came from like negative, it's gonna be 7 Pascal. Both answers are correct. The final answer for stress is equal to 4 times 10 power 7, and the tension and the force is unknown. Question 2, we have 2 unknown. Stress and force needed to cause the stress, which is tension. Now we have to find, this is branch A. Branch B, screen this question. Branch B, guys, look. In branch B, what is unknown? We don't have branch A and branch B, but in this question we have 2 unknowns, stress and tension. We found stress, now we are finding the tension. Stress is equal to what? Tension over area. Tension is equal to what? Rearrange stress times area. Do we have stress? We didn't have, but we found 4 times 10 power 7. Do we have area? Also, we didn't have area, but we found area. 0.785 times 10 power negative 6. 0.785 times 10 power negative 6. Tension is equal to what? 10 power negative 6 is with 10 power 7, it's going to be 10 power 1, and 4 times 0.785 is equal to 3, approximately is equal to 30 or 31, sorry, 31.4 Newton. The amount of tension is 31.4 Newton. In this way, you can determine both stress and tension in question 2 that related with the question 1 in practice 2b. Guys, we finished this section now. We are solving the questions of the section review. What is strain in the wire of length? Wire of length, it means that initial length. Compressed by 0.05. Guys, the word of the compressed, it means that elongation. What do you mean by compressed? It means that the elongation, L minus L naught, is equal to what? 0.05 meter. What is unknown? Strain. Strain is unknown. Strain is equal to what? It's very easy. Elongation divided by initial length. Do we have elongation? Yes. Compressed, it means that elongation. Be careful, okay? 0.05 divided by 0.4, which is equal to, divided by 0.4, 0.125 unitless. Guys, be careful. It has no units. Question 2 in section review. A metallic wire is under tension. Question 2 in section review. A metallic wire is under stress. Sorry, this is 10 power 7. It's not written here. A metallic wire is under stress, not tension. This is stress. The amount of stress is given 2 times 10 power 7 Pascal. What force? What do you mean by what force? Tension causes the stress in the wire if cross-section area is 1.5 millimeters square. So the trick of this question only in the unit. Guys, be careful. Pay close attention. The area was given in millimeters square, not allowed solving with millimeters square. How can you convert millimeters square to meters square? Let's go back to other slides. Guys, look. How can we convert millimeters square to meters square? Multiply 10 power negative 6. This is very, very important, guys. Be careful. Not allowed solving question with millimeters square. How can you convert millimeters square to meters square? Multiply 10 power negative 6. Area is equal to 1.5 times 10 power negative 6 meters square. How can you determine tension? It is very easy. According to the equation of stress, tension over area. Rearrange this equation. Tension is equal to what? Stress over area. Do we have stress? Yes. 2 times 10 power 7 area. After converted, 1.5 times 10 power negative 6 is equal to something. Now I'm going to write 2 divided by 1.3 times sorry, it's not like this. Sorry guys, I do apologize. Stress is equal to tension over area, okay? Tension is equal to what? Sorry guys. Stress times area, times cross product, okay? Tension is equal to what? Stress. We have stress was given 2 times 10 power 7 area, 1.5 times 10 power negative 6, 2 times 1.53. 10 power 7 times 10 power negative 6 is 10 power 1. Tension is equal to what? 30 Newton. The amount of tension is equal to what? 30 Newton. This is question 2. We determine the amount of tension by giving the stress and the area. Only we had the problem with the area because the area was given in millimeters square. You have to convert to meters square. The last question, guys, question 3. Given a bronze wire of length, this is initial length, question 3. Initial length was given 2.5 meter. Cross-section area was given 6.5 times 10 power negative 7. Guys, this is negative 7, okay? Meter square. The area was given in meter square. Does not necessary to convert because it was given in the SI unit. What is the elongation of the wire? What is unknown? Elongation of the wire. If it is stretched under the force 10 power 3, tension 10 power 3 Newton, which is equal to 1000 Newton, okay? Young's modulus was given 10 power positive 11, not negative, guys. Was given in the book is 10 power negative 11, but actually this is not negative 11. This is 10 power positive 11. Newton per meter squared. Corrected this mistake in the book, okay? It was written like this in the -11, but actually this is not -11, this is +11. Youngest modulus was given, guys, 2 times 10 power 11 Newton per meter squared. Now we try to determine the amount of elongation. How can you determine elongation, guys? If you remember, according to Hooke's law, tension is equal to K elongation. Rearrange this equation. T over K. Do we have T? Yes. Do we have K? No, we don't have K. So that is why we cannot determine the amount of elongation by using Hooke's law. Why? Because K also unknown. Not allowed to unknown in one equation, okay? So we have to think about another equation. Because the youngest modulus was given, so that is why you have to use the equation of youngest modulus. The equation of youngest modulus is equal to what? Tension times initial length, A times elongation. What is unknown? Elongation. Change their positions. It's gonna be like this. Elongation is equal to what? Tension times initial length, E times area. Look, do we have tension? Yeah, thousands. Do we have initial length? Yes, was given 2.5. Divided by, do we have youngest modulus? Yes, 2 times 10 power 11. What about the area? Do we have area? Yes, the area was given 6.5 times 10 power -7. Okay? So by calculator you can determine the amount of elongation, which is equal to now I'm going to calculate 1000 times 2.5 is going to be 2500, and 2 times 6.5 13 times 10 power 11 10 power 7 is equal to 10 power +4. So 2500 divided by 13 is equal to 192 times 10 power -4. Okay, and also if you convert to the decimal number, it's gonna be 0.192 meter. This is the amount of elongation in this question. Okay, both answers are correct. 192 times 10 power -4 or 0.192 0.0 192 meter. Okay, both answers are correct. Okay, guys, we finished this chapter 2, and inshallah in the next lesson we are solving the questions in the chapter review. But I would like to solve this question before finishing this lesson. Look at question 36, guys. Question 36. Consider 2 identical springs. How many springs do we have? 2 springs. Each of initial length, the initial length, this is question 36 in chapter review. Initial length was given 300 millimeter, okay? And constant K, spring constant was given K. 400 Newton per meter, okay? Calculate the elongation of each springs. Calculate what? Elongation. Elongation is unknown. Elongation is unknown. For the first case, when they are connected in each of the figure below, the figure must be given in the question. How many figures do we have? 2. One of them series connection, and the other is what? Parallel connection. For the first one, series connection. The second one, parallel connection. In the series connection, the 2 springs are connected in a series connection with the tension was given 10 Newton. So in the series connection, so should I divide the tension by number of springs? No, guys, be careful. In the series connection, does not necessary to divide the tension by number of springs because it was connected in a series connection. According to Hooke's law, guys, how can you determine the amount of elongation? Tension is equal to K times elongation. Elongation is equal to what? Rearrange. What we have with elongation? K. It goes to the denominator, and what does remain in the denominator? Tension. Look, Do we have tension? Yes, 10. K, 400. Elongation is equal to what? 10 divided by 400 is equal to 0.025 meter. In the second part, when it is connected in parallel connection, okay? Look, the two springs are connected in parallel connection. The tension is still 10 Newton. Both cases, they have the same tension. We have two springs, the same material, the same cross-section area, but different in what? Different in connecting. The first part of the question connected in series connection, and the second part connected in parallel connection. If you remember, in parallel connection, you have to divide this tension by number of springs. Tension is equal to T given divided by number of springs. How many springs do we have? 2. T is equal to what? Tension 10 divided by 2 is equal to 5 Newton. So we have to use this tension, okay? Guys, look. Now the tension is equal to what? 5 Newton. Why? Because we have to divide it by number of springs in the case when the two springs or three springs are connecting in parallel connection. When the springs are connecting in parallel connection, you have to divide the given tension by number of springs. In this case, how many springs do we have? 2. So that is why we divided by 2. Now you can use the equation of Young's modulus, K times elongation. Elongation is equal to what? T over K. T is equal to 10 or 5? 5. Don't use this 10, guys, be careful. Divided by 400. Sorry. Dividing by by 400, 5 divided by 400 is equal to 0.025 meter. So we can see that the elongation of the two springs that are connected in a series connection has more elongation comparing with the parallel connection. This one has less elongation. This is 0.01, this is 0.02, this is 0.012, 0.025, okay? Elongation of the series connection is more than the elongation of a parallel connection of the same springs and same tension, but different connection, okay? Guys, that's all for today. We are running out of the time. Inshallah, in the next lesson, we are continuing explaining the chapter 3, and inshallah, we are solving the question of the chapter review in chapter 2. Thank you for listening. Keep up your best doing.